Okay, good morning, everyone. We are carrying on our examination of evolutionary epidemiology today. And if you recall in the last lecture, we introduced some compartmental models of infectious diseases. Some of you may have met these before. This is where we're breaking down a population according to, say, something like their disease status, typically. So individuals who are maybe susceptible, infected, or recovered. That's a classic SIR model. We actually looked at a more simple version of that where there's no long-term immunity, which is an SIS model. So people recover from disease and then they become susceptible once more. So we looked at this model and we learned a little bit about the basic reproduction number R0, which tells us something in an epidemiological sense about whether an infection is going to take off. So whether we're going to get an epidemic in a population. This R0 was the expected number of infections produced by an average infectious individual in an otherwise susceptible population. So if everyone in here was susceptible, one person was infected, how many people do we think that person is going to infect on average? Typically, we think of these things in much larger populations, though, than just, say, something like a classroom. Okay, so that R0, if R0 is greater than 1, then the pathogen is going to take off. We're going to have an epidemic. If R0 is less than 1, we're going to have an exponential decay of infections, and it's going to decay to 0. We're not going to get an epidemic. So that's an epidemiological sense, but actually, in many cases, but definitely not all, depending on how the model is structured, this R0 can serve sometimes as a proxy for pathogen fitness. In other words, when we looked at doing the full adaptive dynamics of our model, we found that a singular strategy that gave us our optimal level of virulence. This happened to be a CSS. That's why we know it's an optimal level of virulence. In other words, it's an evolutionary maximum. If you like, it's a fitness maximum for our pathogen, and we converge towards that. That singular strategy, that's a CSS, also happens to maximize R0 in that particular model. Okay, so what that means is that while R0 is not fixed at fitness, evolution is essentially maximizing the same quantity. So that's quite nice because sometimes if we know something about the models, we might be able to jump straight to the R0 rather than having to necessarily go through all of the standard adaptive dynamics analysis. We also talked a little bit about trade-offs, in particular an idea of a trade-off between transmission and virulence. I'll talk a little bit more about that in a moment. And we talked about how ultimately this can lead to different levels of virulence evolving. Yes.
Aren't SIS models like unrealistic because we don't have a recovered?
It depends on the infection, right? Because, for example, many sexually transmitted infections, things like gonorrhea, chlamydia, there's no long-term immunity from those diseases. So you recover and you're immediately susceptible again. Many invertebrates and plants and things like that as well, they don't have adaptive immune systems. So the reason we gain immunity typically is because we have two levels to our immune systems. We have an innate immune system and an adaptive immune system. And that adaptive immune system is your antibodies. So they recognize pathogens. It takes a while for that to ramp up. But once they recognize the pathogen, then if you get infected or challenged by that pathogen again, they can bind to it and you don't get a meaningful infection. But in things like plants, they don't have those antibodies, and likewise in many insects as well. So they get infected by something. If they're able to recover and clear it through their innate immune system, then they become susceptible again, typically. So yeah, it depends. If you kind of take yourself slightly out of the human-centric view of like pathogens and think more broadly about the natural world, you end up seeing that things like an SIS model is definitely more common. Yeah, very good question. Okay, so yeah, we're going to continue talking today about pathogen evolution. We're going to talk a bit more about evolution of virulence in a slightly different context and see what happens. Essentially, what happens if we tweak some of their assumptions that go into our model, what happens to evolution of pathogen virulence. And then later on, we'll talk in the second half about interventions. So interventions are things that we might do to try to manage infectious diseases. Typically, people think about this from just trying to control, say, numbers of infections or the growth rate of an infectious disease. But we're going to take a sort of evolutionary lens to this and say, well, how might interventions affect pathogen evolution? Okay. So by the end of today, you should know what I mean when I say density-dependent mortality. We've already discussed this idea of a trade-off, but you should know a little bit more about this in general. I mentioned briefly this concept of an eco-evolutionary feedback. This is really just the idea that in these adaptive dynamics models, our mutant is always invading a population that is determined by the current resident, right? Remember, our invasion fitness is a function of two variables, our mutant trait and our resident trait. That means that the ecology, if you like, or the epidemiology of our system shapes the evolutionary dynamics, but likewise, the evolutionary dynamics feedback and shape the ecological or epidemiological dynamics. So there's this kind of feedback loop that exists. That's what I mean by an eco-evolutionary feedback. And I mentioned we'll talk about drug resistance as a form of intervention later on. Any questions before I get started? Okay, so we're going to jump back into our SI model. I said it's an SIS model. Technically, this is an SI model because there is no flow back from this I class to this S class. So previously, when I first introduced this, we had a plus gamma I here and a minus gamma I here. This would give us an SIS model that looks like this. Individuals become infected, and then they can recover. But if we scrap this recovery term, then we end up scrapping this arrow here. Okay. Now you could argue that this is even less realistic. There are cases where people get chronically infected by things and they can't recover from them. Again, many diseases, if we think outside of a human population, in plants and animals, once they get infected, they can't clear these things. So it's not unrealistic, but you have to always think about when does this apply to a particular scenario or not. The reason we're going to assume that gamma is equal to 0 is just because it makes the math a lot easier.
Would this have been good to use during the Black Plague before becoming the cure then? Things like that. Yeah, essentially, like if you're getting infected by something and there's no chance of recovery, then yeah. So yeah, this is kind of done mainly here for mathematical convenience. One of the things sometimes we do, if we might simplify a model to do our analysis and get as far as we can kind of algebraically and understand what's going on. And then maybe you add in recovery terms here, for example, or some more biological realism when you simulate it or solve it numerically. But yeah, for the purposes of today, we're gonna keep things as simple as we can, just so we can make some progress on the math side. Okay, so just a reminder of what the terms are here. So we have a birth term here, B, which could be a function of S and I. We have a transmission rate beta, which we're assuming is a function of alpha, and alpha is our level of virulence or disease-associated mortality. Yes?
Can't we always reduce the system of ODEs by 1 by using the density requirement?
As in have set it to proportions rather than not necessarily, because here you can do that if the population size is constant, but here this birth rate function means that the population size won't necessarily be constant as disease is spreading, right? It'll obviously, if it reaches a stable endemic equilibrium, then it's at a constant population there, but in general, like if you perturb it away, it won't be a constant population. Yes, we can do that, and in fact, later on, if I remember rightly, in today's model, we will be doing that for the drug resistance example. Where was I? Okay, so we have this trade-off between transmission and virulence. I'll talk about that a bit more in a moment. We've also got here a death rate D. Okay, and that's that death rate D is essentially everything other than disease. Okay, and like I said, we've set this recovery rate here again to be 0, just to keep the math a little bit simpler. So I mentioned this idea of trade-offs a couple of times now. We discussed this last lecture, and we just said, okay, we're just going to assume that more transmissible pathogens are more virulent. So to go into this a little bit more detail, or as a reminder, because I did kind of say this last time, the kind of motivation behind this transmission virulence trade-off is that pathogens have to infect cells and consume host resources in order to replicate, in order to grow within the host. And so they want to obviously grow within the host, and then they can produce transmission stages, whatever those transmission stages look like. They might just be copies of themselves. And in order to pass those on to another individual, they have to create those. Therefore, they have to be infecting host cells and causing damage. Logically, it kind of stands to reason that the more that they replicate, the more likely they are to be able to transmit, the more transmission stages they're producing, but the more damage they're causing to their host. Okay, so we might expect there to be hosts that have a high pathogen load. This idea of a pathogen load can think of just as the the total burden of a pathogen or even just the total number of pathogens inside, that they'll be more infectious to other hosts. So they have a high transmission rate associated with a higher pathogen load. And then hosts that have a low pathogen load have a lower transmission rate. So in other words, we should expect some positive relationship. And so why does this trade-off matter? Well, our analysis, if you recall from the previous lecture, indicated that if the transmission virulence trade-off exists, then its curvature has a major impact on our outcome, our dynamics that we expect to see. So what do I mean by this? Well, let's consider a couple of examples. I'm just going to sketch a couple of graphs here of our virulence varying alpha, that is on the horizontal axis, and then beta of alpha on our vertical axis. Okay. So suppose we have a situation that looks something like this. So here we find our singular strategy, wherever it happens to be, some alpha star. Can anyone tell me what is going to be the sign of the curvature at alpha star? Can it be positive or negative?
It's gonna be
Negative, yeah. So this is negative. And we had our E, our evolutionary stability in the last lecture, was actually proportional to beta prime alpha star. In other words, it actually had the same sign. Maybe let's write that in. This was equal to this times by, if I remember rightly, S star. Okay, so if this curvature is negative like this, then our evolutionary stability is going to be satisfied. And so on the left-hand side here, this would be an evolutionarily stable strategy. So it's a continuously stable strategy as well, because we also found that C was equal to E in this model. Okay. So like biologically, what's the intuition behind this then? Well, it kind of says that suppose you start off with a level of virulence down here, that's your alpha naught. This is saying, okay, suppose I increase my virulence a tiny bit over to here. I get a relatively large increase in beta. So you can think of this as being my beta naught, and then a beta 1, and an alpha 1, right? So if we shift ourselves up this curve, this is a relatively large increase compared to our change in virulence. So you're kind of gaining a lot here. You're gaining a lot in transmission. You're not sacrificing a lot in terms of virulence. So just to make it clear why this is a cost, virulence is a cost. Our R naught, if you remember, looks something like this: beta of alpha times by S star. Technically S at the disease-free equilibrium over alpha plus D, and plus gamma if you have that there as well. So, you know, from the pathogen's perspective, it wants this R naught to be as big as it can, right? So it needs to increase its beta of alpha as much as it can, but as it increases alpha, it's also going to be increasing the denominator, right? So there's a balance here between these things. Okay, so if it's able to increase its transmission rate by a substantial amount, then it doesn't matter if alpha is on the denominator, okay? It's offsetting this. If you then compare this to a situation over PSA, suppose now this was my alpha naught and this was my alpha 1. Kind of hard to see, but I'll sketch it over on this side. Here, roughly the same increase in alpha leads to a relatively small change in beta. Okay, so it's paying the same cost, if you like, in terms of increasing its virulence, but it's only getting a tiny bit of an increase in transmission. So what this means then is that there are diminishing returns, or in other words, the costs accelerate. So you sometimes see these things written down. We say that the costs accelerate. In other words, we have diminishing returns. as alpha increases, the benefits of increasing alpha further are decreasing. This, you can think of this therefore as being sort of a balancing selection, right? Because on the left-hand side of this alpha star, we're getting it's good to increase alpha. You get a relatively large increase in beta. On this side, a large increase in alpha or a normal increase in alpha leads to a very small increase in beta. Therefore, we should be selecting against higher virulence. What it does then is it kind of pushes us, therefore, towards this alpha star in the middle. Okay. This gives us our CSS. Now let's think about what happens if we change the curvature. Maybe it looks something like this now. Again, we can think about what an alpha star might be on this curve. And here, our curvature is going to be positive. So all we're essentially doing now is reversing the argument that we had before. Suppose we are on this right-hand side of my CSS. We increase alpha a little bit. We get a relatively large increase in beta. So a relatively small increase in virulence leads to a relatively large increase in transmission. So you'd be expecting selection to push us away from alpha star. In other words, alpha to be increasing. Okay. Conversely, if we are on the left-hand side, a relatively small increase in alpha leads to, or sorry, a relatively sort of normal change in alpha, if you like, compared to this brown one over here, leads to a very small change in beta. So here it's likely to be costly. In other words, selection drives us now away from this alpha star. So can anyone tell me what it would be? What kind of singular strategy would alpha star be? Yeah.
So now we have a repeller situation.
Yeah, exactly. So this one on the left-hand side was a CSS, and this is a repeller. So you can see that the shape of the trade-off can have a really big impact on your qualitative outcome you expect to get. Okay. In fact, it doesn't matter the extent to which, in this case, the curvature, like it doesn't matter how much this is accelerating. It just matters that it is accelerating. Likewise, it doesn't matter how much here our costs decelerate. It just matters that they do decelerate. Okay. So this one on the right-hand side, we have accelerating costs here on the left and decelerating costs on the right. In other words, we have increasing returns. And we can see these types of trade-offs. We're talking about transmission and virulence, but these types of trade-offs exist for many, many different types of traits. Yes.
I do have a question with the repeller situation.
Yeah.
Like I can understand how like if your alpha value is above alpha star, then it would increase over time.
Yeah.
Like I'm not entirely sure how like if it starts below that it would cause a decrease in feedback loop.
Okay, yeah, because so below this, I mean, it's the same argument essentially as up here, right? Because all we've done essentially is just kind of like flip this curve round. So here and here, a sort of unit change in alpha leads to a very small decrease in change in beta. If I was to, I'll tell you what, let me do it on this slide here. Suppose I take a really extreme example. Suppose my curvature looks something like this. Okay, really quite a very shallow but decelerating cost here. If now and I'll flip this around as well. Suppose I start here, alpha naught and alpha 1. Okay, so this is a pretty big change in virulence, perhaps, right? But my change in my change in transmission might be quite small. Okay, so if I go back to my R naught, which I had down here, I might reduce this a little bit, but I might reduce this a lot by reducing alpha. Okay, in other words, I make my denominator smaller, even though I've made my numerator a bit smaller, making my denominator a lot smaller is going to make R naught bigger. Yeah. Does that help? Yeah.
I think I understand.
So like I said, these trade-offs exist for many traits. I've used this example of transmission and virulence here. There's a bit of debate about the extent to which this trade-off actually exists. People tend to assume this kind of trade-off exists here, partially because if you don't assume this kind of trade-off, that means that you either send things off to zero, so pathogens evolve in the long term to not be virulent at all. So virulence here should tend towards zero. And over here, this would mean that virulence would just increase, and we'd have runaway selection for higher and higher levels of virulence. We don't tend to see either of these things. You sometimes see that pathogens become less virulent. Sometimes their virulence goes up, but we don't really know generally where a pathogen is going to lie on these curves. Okay, so typically we actually assume this kind of accelerating trade-off just because we would expect pathogens to evolve to some intermediate level of virulence.
So would like a good example of a repeller be like influenza? Because like not many people die from.
It's kind of hard to say for like specific. Well, the problem with the repeller is it means that you could be on the other side of this, right? And you could get sent off to an infinite level. I mean, this idea of what should happen to virulence has actually been like a long-standing debate in sort of evolutionary biology and evolutionary epidemiology. One of the sort of common things people say is that they'll say, "Oh, pathogens don't want to kill their hosts," right? And that's in some sense true if we apply some agency to pathogens. And so people have argued before that pathogens should always evolve to be less virulent. But they haven't thought about, in that case, what trade-offs might exist. Okay, so if there was no trade-off on, I'll just go back up to here actually. If this beta of alpha was just a constant, if we just had beta on here, you would expect alpha to evolve to zero, right? Because this will maximize R naught. But if beta is a function of alpha, then you might have a situation where here beta increases with alpha. Your R naught, if you were to then sketch it out, versus alpha, would end up looking something like this, perhaps. And so when people say, and people said this with COVID, for example, they're like, "Oh, don't worry, it will become less, it will evolve to be less virulent because pathogens don't want to kill their hosts." Well, that's assuming that you've landed on this side of the curve, right? If you happened, when COVID jumped into the human population or any pathogen comes into the population, if it's on this side of the curve, then sure, you'd expect it to maybe evolve here and it becomes less virulent. There's no guarantee that's the case, though. Perhaps the first sort of strain that jumps into humans is over here. A priori, you don't know where you're going to be on this curve. Okay. If anyone's interested in economics, this is a little bit similar to the idea of a Laffer curve. Does anyone know about the Laffer curve? This is the idea that if you tax people and corporations at 0%, you get no tax revenue. If you tax them at 100%, no one's going to do anything, so you get zero tax revenue. Therefore, there should be some intermediate optimal level of taxation. Essentially, people on the left-hand side of the spectrum, if we now switch this from R naught to taxation, people on the left side assume we're over here, and people on the right-hand side of politics assume we're over here. This is just ideologically, people say, well, we should reduce taxes because it increases your revenue, and that's good. And here people say we should increase taxes and it will increase your revenue. Without more data, you can't actually say a priori where you would sit on that curve. And it's a similar thing with pathogens. When they first come in, we don't know really where they're going to be. Okay, I'll leave politics at the door, probably for the best. Okay, so let's think about what happened. So in the last lecture, we had this scenario on the left-hand side. Well, we actually showed both scenarios, essentially, right? We only found that you could get a CSS or a repeller with our particular model of virulence evolution, okay? So one of the things that we do observe in nature is that, within sort of different strains of a pathogen, say something like COVID, there will be strains that are more virulent and strains that are less virulent. And sometimes these strains are able to coexist with each other. But our previous model basically just said there's one optimal level of virulence. And of course, there are many reasons why something like COVID-19, there are other reasons as to why they might be able to coexist. So we'll just get that off the table to start with. For example, whereabouts the pathogen tends to infect more. Does it tend to be up in the upper respiratory tract or the lower respiratory tract? Will have effects on transmission and virulence. We're not going to account for all of these kinds of things. But in general, we might want to see how does changing the structure of our models, and therefore the assumptions about the underlying population dynamics, affect whether we get something like evolutionary branching or not, which we didn't see at all before. And this kind of also demonstrates that a slight change in your model can maybe change your assumptions. So it's always important when you're doing any kind of modeling to think about how your assumptions might affect your results, okay? So let's think about a slight variation to our SIS model. We're now going to have a constant birth rate B. And we're going to assume as well that only susceptible individuals reproduce, so infected individuals don't reproduce here. We still have a transmission virulence trade-off, beta of alpha, and density-dependent transmission SI. Now we're going to assume that our death rate looks like this. Our natural death rate is minus D times by N times by S. I'm going to put this in brackets just to emphasize that this is our death rate here. And dIdt is going to be our infections, beta of alpha times SI, minus D times by N plus alpha times by I. So does anyone have any idea what this model assumes differently to the previous one? Yeah.
I guess the death is dependent on the number of individuals.
Yeah, so we've shifted our density dependence from our birth term. So if we go all the way back up to the beginning here, this we had typically assumed was density dependent before, and the death rate, the background death rate was density independent. We've now changed this around. So now we have density independent births, but we have density dependent deaths. Okay, so maybe as individuals compete more strongly for resources, the death rate goes up. Okay, whereas previously we were assuming the more strongly they competed for resources, the more their birth rate went down. Okay, both might be reasonable assumptions in different scenarios. Okay, so we've got density dependent deaths. Okay, so whenever we do any sort of, we're going to essentially do the same as we did before, look at the evolution of virulence in this model. As always, the first step is that we should check to see that we have, in the case of a disease model, a stable endemic equilibrium. In other words, the disease is maintained in the population. If it's not maintained in the population, it dies out, then nothing can evolve, right? We want our pathogen to evolve, or at least we want to see how it will evolve. If it's not present, it's just gonna, we have a trivial answer. So we should start, first of all, by determining if our population will tend towards a locally asymptotically stable, non-trivial equilibrium as t tends to infinity, okay? This is kind of laborious to do just because of changing the structure of the model means that finding the ecological equilibria is harder. So this change in demographics, so demographics is all about births and deaths, essentially. It makes this rather cumbersome, like I say, so we're going to skip over this here, okay? But just like before, we have three possible equilibria. One is a trivial equilibrium at 0, 0. So this is trivial because there are no hosts, therefore there can be no pathogens. Everything is at 0. Nothing can happen, either ecologically or evolutionarily. We have a disease-free equilibrium, just like before. And this, in this model, happens to occur at B over D for our susceptible population and 0 because there's no pathogens. It's a disease-free equilibrium. And then we also have an endemic equilibrium, I refer to as EE. This one's a little bit more complicated. Don't worry too much about writing this down. I'm writing this down just so we can refer back to it later. This is for our susceptible class here. And our infected class This is typically what happens because you've got things coexisting. The algebra becomes a little bit more messy here. Exactly what these are doesn't really matter in the context of here. It's not like you need to memorize these things. I'm just writing this down so we can refer back to them later. Okay, it's also possible to show that when our pathogen is viable, in other words, when our R0 is greater than 1, our endemic equilibrium is locally asymptotically stable. Okay, so here, obviously one needs to consider a condition here that makes this viable. In other words, this needs to be positive. Numerator. This ultimately tells us our R0. There is another way we can calculate our R0 though. We can do this by, we just go back up to our equations here, considering a little bit like when we do our invasion fitness. When can the pathogen invade when it's rare? In other words, when we're at our disease-free equilibrium, when can this pathogen invade? That's the same as finding when our disease-free equilibrium is unstable. So for our pathogen to invade, we need its per capita growth rate when it's rare to be greater than 0. So what is this per capita growth rate when it's rare? Well, it's going to be beta of alpha times by S star, and I'll refer to this as S star at the disease-free equilibrium, or DFE. So we're clear on what equilibrium we're talking about. The I that we had here before has been, we're dividing by it, because we're talking about a per capita growth rate. We had a death rate minus dn before. Because we're assuming that the pathogen is rare, n is just going to now be S star at our disease-free equilibrium. And then we had minus alpha as well, which is our virulence. So this has to be positive in order for our pathogen to be able to invade. Like I said, when our pathogen is able to invade, it turns out that this also means that our endemic equilibrium is stable. So we can do a little bit of rearranging here. Take these terms over to the right-hand side, divide throughout. We end up with R0 is equal to beta of alpha times by S star at our disease-free equilibrium, divided by D times by S star at our disease-free equilibrium, plus alpha. So R0, we can simplify this a little bit further. Our disease-free equilibrium up here is just this B over D. So now this should simplify to B times by beta of alpha over D times by B plus alpha. And we need this to be greater than 1 for our disease to be able to invade, and in turn for our endemic equilibrium to be locally asymptotically stable. Just remember, we refer to this R0 as our basic reproduction number. Okay. What I want you to do now is find a pathogen's invasion fitness and its selection gradient, and then an inequality for evolutionary stability in terms of our endemic equilibrium. So don't substitute in our endemic equilibrium because things will get kind of messy. So just do this, and also your evolutionary stability here will be in terms of your singular strategy alpha star. Don't worry about finding that now. Just find expressions for your invasion fitness, your selection gradient, and then an inequality for evolutionary stability, okay? Okay, so your invasion fitness is going to be a function of alpha m, our mutant virulence, and our resident virulence. Remember, for our invasion fitness, all we need to do is we need to look at this equation here, which is our equation for our infected class. We don't have to do the next generation method or anything here because we've just got one equation describing our growth of our mutant trait. So I'm just going to copy this. Okay. Our invasion fitness is just going to be the per capita growth rate of our mutant trait when it's rare. So first thing we need to do is we need to just substitute in our mutant trait. So we have IMs and alpha Ms. And then we need to evaluate this at our residence equilibrium. And then we're going to divide through by our mutant population size, IM, because we want its per capita growth rate when it's rare. Note that this S star, just going to put E here and under our N star as well. This is not our disease-free equilibrium anymore because our pathogen is invading a population that already has a pathogen in it, okay? That's our invasion fitness. Our selection gradient, I refer to this as little s here, just to distinguish it from big S. This is going to be our derivative of invasion fitness with respect to alpha M, and then evaluated at alpha. This is going to be therefore beta prime of alpha minus by S star EE minus 1. So this D N star drops out. The fitness is here linear, the second term is linear in alpha M, therefore we just end up with a -1. And then our evolutionary stability is going to be satisfied when our second order derivative with respect to alpha M evaluated, everything evaluated our singular strategy. Here we just now take our second order derivative of beta, evaluated at alpha star, and then we have S star as well. Remember that this S star is evaluated itself at alpha star, okay? We usually don't write this as, we usually don't write this here as S star of alpha star, but that's one way of thinking about this. Likewise up here, this is an S star EE of alpha, yeah. Okay, so we've got these three equations here. Typically, we can always sort of, if you can write down expression for invasion fitness, generally you can take the derivative to find your selection gradient, you can find your second derivative with invasion fitness. Because it never affects, the mutant trait never affects the ecological equilibrium, you can always just leave these here in at this stage and substitute them in later when you're finding your evolutionary stability. So finding these three tends to be pretty simple. The problem tends to be when you find your convergence stability, which we'll get onto in a minute. So one thing to note is that the selection gradient here looks basically the same as what we had before. Remember, we had a selection gradient last lecture that looked like this. We had evolutionary stability that looked like this. There are key differences here, though, in terms of this S star here. And that's because this S star is going to be changing now. It's not going to be the same as it was before because the underlying model has changed. Okay, so even though these equations look the same, we're not necessarily going to get the same outcomes. This links back to this idea of an eco-evolutionary feedback as well. Okay, so the model has changed. That also means as well that the level of virulence changes. Our singular strategy is going to change because it's going to depend on this eco-evolutionary feedback. One other thing to note is that, again, our evolutionary stability is all here again determined solely by the curvature of our transmission virulence trade-off function. So in other words, this S star is always going to be positive. So our curvature of our transmission virulence trade-off, again, is the key. Just like we had back in these graphs up here, the curvature is going to be the key thing to determining our stability in terms of evolutionary stability, that is. Okay. How about convergent stability? Well, actually, just one more thing. Just like before, if this the curvature of this this trade-off is negative at our singular strategy, then our singular strategy is going to be evolutionarily stable. Okay, otherwise it will be evolutionarily unstable. How about convergent stability? Do you remember when we talk about, convergent stability? This is given by two terms. I'll refer to one of these as being M. The other as being E. So E is our evolutionary stability. M, we're not going to get onto this really. We don't kind of run out of time to discuss this in the course, but this is actually referred to as mutual invasibility. It's actually telling us something about a different characteristic about our populations here. For this M is just our cross derivative, our second order cross derivative with respect to alpha M and alpha, and again evaluated at our singular strategy. When you work this out, we end up with minus D times by B beta of alpha minus D, all in brackets, minus alpha times by D, all over alpha times by beta of alpha plus D plus BD. Okay, so the numerator here, sorry, the denominator here is always going to be positive. So all these terms here, function is positive as well. What about the numerator? Well, it might not be immediately obvious, but this here, we go all the way back up, it's the same as what I've highlighted in green here, which is nice because we know that our endemic equilibrium is only going to be realistic if this is positive. And we're evaluating at everything at our endemic equilibrium. So this is a prerequisite. So that has to be positive. So the term down here in green also has to be positive. Our denominator is positive, and this term out the front is going to be negative. So this is always going to be negative if our endemic equilibrium is realistic. This is a bit different to the examples that we've seen before, where we've often found that this M here was equal to 0. And just our convergent stability was determined by evolutionary stability. That's what we had in the last lecture. Here, because we changed the structure of the model, it's actually changed this cross derivative here. And now we find that this M is always left negative. So convergent stability will depend on the sign of E. Because this M is always going to be negative, and this E could be positive or negative depending on the curvature of our trade-off. If the curvature of our trade-off is negative, then it's going to be convergent stable and evolutionarily stable automatically, right? Because M is negative as well. But it's possible, depending on the relative magnitudes of M and E, that it might be convergent stable if M has a higher absolute value, it's higher magnitude than E. It could be convergent stable, but evolutionarily unstable. In this scenario, we'll get a CSS. But if it's evolutionarily unstable, then we'll get a branching point potentially. It could also be a repeller. Okay, let's take a break there. Okay, we got up to talking about convergent stability, and we found that it is possible in principle, depending on the functions that we choose. In this model now, this term M is not equal to 0 like it was before, it's always negative. And we know that it's possible to choose, depending on the curvature of our transmission virulence trade-off, it's possible to choose functions where this E could be negative or it could be positive. So depending on the relative magnitudes of these things, it should be possible to choose a function where M is negative, E is positive, such that C is negative still, okay? It's just changing the magnitudes of these things. So what we're going to do is going to go through an example of this and then see whether we can, in principle, get evolutionary branching. So let's consider a trade-off that looks like this. Beta of alpha is going to equal some constant c plus m times by alpha. You can think of this as being some linear term here. And then we're going to add on sigma times by alpha minus alpha star squared. We're kind of cheating a little bit here because we're kind of jumping ahead and we're saying this alpha star usually we find later, but we're fixing our trade-off. So ultimately at alpha star, this term will go to 0. Okay, it's a little bit of a cheat. But we're doing this just because we want to see in principle, is it possible to get it to branch? Okay, so these constants I've introduced, Cm and sigma, are all positive. And then it's pretty straightforward to find out what our derivatives of beta are with respect to alpha. Our first order derivative is going to be m plus 2 sigma times by alpha minus alpha star. And second order derivative is going to be just 2 sigma. You note that I've chosen this. If sigma is a positive constant, our curvature at our singular strategy is always going to be positive. Okay, because the curvature everywhere is going to be positive. Okay, that's nice because remember our evolutionary stability here depends on the sign of beta double prime. So this is going to be positive, so it's going to be evolutionarily unstable. So what do we know from our selection gradient? Well, our selection gradient, let's just take it all the way back from up here. Where is it? Up here, this is our selection gradient here. So our selection gradient at our singular strategy must satisfy this right-hand side being equal to 0, evaluated at alpha star. And to help, I'm just going to put alpha star here as well. Just to remind us that this endemic equilibrium is a function of alpha star. This must equal 0 at our singular strategy. We've just worked out what beta prime is, so we just need to substitute that in. So beta prime was up here. We have m plus 2 sigma times alpha minus alpha star times by s star of alpha star must equal 1. We also know that because we've already set alpha equal to alpha star, this is actually going to be 0. We just end up with m is equal to 1. And we've already established that it's evolutionarily unstable because beta double prime of alpha is positive. Okay, so this implies that E is negative. Now, ordinarily, the last thing to check is our convergent stability. This turns out to be a bit of a pain to do. Again, we're going to skip off over this stage here. You can also do this numerically. I don't want to spend 20 minutes basically going through the lengthy derivations that don't teach you anything. And take it on faith here that this is convergent stable. We can show this numerically and we can verify it through simulations. I'll advise as well when it gets to the project, while I want you to say find convergent stability, I wouldn't recommend doing those things by hand. Okay, so I want to see what your answer is. I did send an announcement about this as well. I would recommend you use something like Maple or Mathematica or any sort of software to solve the problem numerically, or sorry, solve it algebraically. You can then solve it numerically if you wish to. Okay. So, like I said, we can check either through simulations or we can check numerically. to determine whether our system is convergent stable. And it turns out to be, yes, sorry, question.
Is that like code also to do some just the stuff that created our figures?
No, just the stuff that created your figures. Yeah. Is that a question or is it just a stretch?
Oh, just.
A stretch. Okay, that's cool. Okay, so what happens when we simulate this? Well, we start off down here with some initial level of virulence, call this alpha naught. We see that virulence increases in this case until we reach our singular strategy. And this is a branching point. So our singular strategy is a branching point because it was convergent stable, but evolutionarily unstable with the particular trade-off that I introduced. That means our pathogen now splits into two coexisting strains. One of these is a relatively low virulence strain. The other is a relatively high virulence strain. I believe if you were to carry this on, you'd actually see in this case that one of them would tend towards no virulence at all, and the other one would settle at some arbitrary higher level of virulence. So we've seen that starting from just this one initial pathogen, we've ended up diversifying the pathogen. This is very different to what we saw before in our model from the last lecture. All we've changed, essentially, we've changed the trade-off around here, but like we never found branching points in the previous one before. So the fact that we've changed the trade-off here doesn't really matter in a sense of the key difference between why we see a branching point here and we didn't before was here we've got density-dependent deaths. Before we had density-dependent births. So this illustrates that why it's important to sometimes consider different model structures, because you change your model structure, it can change your predictions for what happens in evolution. Okay, let's move on from evolution of virulence. So far we've been really focusing on what I'd refer to as qualitative outcomes. In other words, showing that the type of singular strategy that we get depends on, for example, the shape of our transmission virulence trade-off. You know, are we getting a CSS, a repeller, a branching point? And also thinking about this idea I just mentioned here, whether hosts births or deaths are density dependent. So we've been thinking a bit about qualitative outcomes and model structure. And I want to focus a little bit on quantitative outcomes. So quantitative outcome here, we're going to think about what happens to the actual level of virulence, our singular strategy, as some key parameter changes in our model. So what key parameter are we going to think about? We're going to be thinking about some sort of intervention. I mentioned interventions at the start. These can take a range of different forms. We might have sort of therapeutics, things like antiviral drugs. We might have vaccines, another type of intervention that we might have to try and control infectious diseases. Also, from the pandemic, we saw extensive use of non-pharmaceutical interventions, things like lockdowns, and masking, general social distancing. These are all public health interventions to try to minimize the spread of infectious disease. So a key question for policymakers that they should consider, but often don't, how will any of their interventions affect pathogen evolution? This was a bit of a bugbear of mine during the pandemic, because when the first variants of concern started coming out, people in public health were going, well, no one could have foreseen this was going to happen. Whereas every evolutionary biologist was going, no shit, it's going to happen. Of course, if you build up immunity in a population, there's going to be selection for immune evasion. Like, this is quite basic evolutionary biology and evolutionary epidemiology. So that kind of evolutionary thinking was clearly not evident in a lot of public health policy in terms of the people that are making those sorts of decisions. I will say, though, one thing that public health policymakers do tend to take into account, they don't necessarily factor in long-term evolutionary outcomes in terms of their decisions. Even epidemiological outcomes that might be, you know, what a model predicts is the best thing isn't necessarily what is going to be put in place. So, for example, it might be advantageous to reduce total disease deaths. You say vaccinate young people who are mixing a lot. That probably would have reduce the overall level of deaths from COVID. But that's kind of untenable because young people don't tend to die from COVID. It's older people. So basically giving vaccines to young people would be politically untenable if lots of older people were dying, even though that would maybe be the best outcome for the population as a whole. And likewise, people might say, well, we have to use lots of antimicrobials now to save patients, even though it might in the long term increase drug resistance. So as modelers, one thing we can do is we can talk about the types of outcomes that we expect, and we can make predictions and give advice, but ultimately that's not the only thing that public health officials will have to take into account when they're making their decisions. So I mentioned this idea of drug resistance. This is a big problem, in particular the evolution of antimicrobial resistance. So you'll have heard of probably pathogens maybe like MRSA, which is methicillin-resistant Staph aureus. So Staph aureus is just a regular pathogen. And then there's MRSA is a particular problem in hospitals. So it's resistant to this particular type of antibiotic. There's multi-drug resistance and even extreme drug resistant TB. Essentially, by using antibiotics like penicillin and its derivatives, we've kind of pushed pathogens to evolve drug resistance. Okay, and this has spread extensively over the last century. Part of this problem as well is that because we're kind of running out of antibiotics and antimicrobials in general, some of these are down to sort of like the last line treatments that we don't have anything else. Okay, so people talk about what's the next pandemic going to look like. There are different types of pandemics that will likely occur. This is a major one because even if you start going in for routine surgery and you haven't got anything to treat simple opportunistic infections, all of a sudden your routine surgeries become really problematic. Okay, so we need to think often how can we maybe use drugs to a certain extent that we maximize patient outcomes, but also try and minimize evolution of drug resistance, or even know how we expect it to evolve. Okay. So one of the things is that drug resistance is typically costly. I talked about trade-offs in the context of transmission and virulence earlier, but there are other types of trade-offs. So why aren't all pathogens just resistant to drugs? Well, it might be that they need to have additional machinery, if you like, cellular machinery to there's things called like efflux pumps to pump out antimicrobials that they might take in. They might have to either gain additional plasmids. Plasmids can encode genetic resistance or resistance against different antimicrobials. Those plasmids themselves can be costly for them to carry, so metabolically costly. So then we might expect there to be some growth costs typically associated with drug resistance. Okay, so it's not just a case of pathogens can just have a free ride and evolve resistance. There's typically some trade-off they're going to experience. One thing though is that obviously when we start to increase the use of drugs, we're going to typically increase selection for drug resistance. That's our sort of naive prediction that we would have, right? If you have no drug use and drug resistance is costly, then we wouldn't expect drug resistance to evolve. We'd expect there to be selection against drug resistance, okay? So it doesn't necessarily mean that using drugs will evolve, but it becomes less costly and potentially advantageous. So what we're going to do is we're going to suppose a pathogen follows SIS dynamics. So before we were doing SI dynamics, we're going to bring recovery back into this. And we're going to have density-dependent transmission like we had before, so a beta SI-like term. And we're going to assume that recovery only occurs when antimicrobial drugs are administered, and that our recovery rate gamma increases as more drugs are administered. So gamma here is greater than or equal to 0. Gamma we can just think of as our level of drug, or as at least correlates with our level of drugs that we're applying to the system, okay? So ordinarily people don't recover, but if you administer this antimicrobial drug, then they're able to recover. We're also going to assume that host demography, in other words, births and deaths, are negligible over the time scale that we're interested in. This would be like assuming that pathogens evolve very, very fast, or the epidemic dynamics settle down very quickly, and your hosts are very long-lived. So this is nice because it allows us to rescale our model. So the S and I are now the proportion of the population that's susceptible and infected respectively. So this is what you were asking earlier, right? We can rescale our model. We can, because we've got a constant population size, there's no demography, no turnover of births and deaths. We can simplify our model greatly. And we're going to suppose that our pathogen may experience mutations that affect its level of drug resistance. We're going to call this drug resistance rho. And rho is going to go between 0 and 1. And it's going to multiply our recovery rate gamma. So when rho is equal to 0, there's no drug resistance. When rho is equal to 1, there's complete drug resistance. We are going to assume, though, that drug resistance has a trade-off. There's a cost here. And we're going to assume that this is a growth cost. So kind of sort of inverse of what was going on before with our virulence. We're now going to assume that that our transmission rate is a function of rho. As rho increases, we're going to assume that beta decreases. The idea here is that pathogen is having to invest resources, divert resources away from its growth, its replication, in order to protect itself from the antimicrobial drugs. This could be as simple as having one of these plasmids that is energetically costly to have or to reproduce. So having the plasmid may confer some level of drug resistance, but then it slows its growth. Okay? Yes?
Is that always the case when we have like mutations that make the pathogen resistant to drug and also have more reproduction rate?
I mean, that is possible, but it depends. Wow, it depends in terms of. So this is like a baseline reproduction rate in the absence of drugs, right? I guess yeah. Like I'd never say never. If it was always beneficial, right? The reason we have a trade-off here is that the outcomes essentially become trivial. If it's beneficial for all of its traits, then selection is just going to favor it, right? In the same way that you might not see variation of population for certain traits if that trait is just universally beneficial. So it is possible as well that things can be initially costly, and then you can have mutations that counteract those costs, and then it's not costly afterwards. This can also be a problem because once you've kind of evolved something like drug resistance, if there are then compensatory mutations to compensate for the costs, then there's no selection to go back when you take the drug away. So there are cases where it might be costly. Okay, so what does our model look like now? So now we're dealing with proportions. So S plus I is just going to equal 1. So we only need one ODE. We don't need to track both S and I, because if you know I or if you know S, you can determine the other one. So now I'm just going to write down my resident dynamics are going to be given by dIdt, which is my transmission rate beta of rho, where rho is my level of drug resistance, times by SI, minus, we're going to have a recovery rate gamma, which is multiplied by 1 minus rho. So this is our amount of drugs that we're giving to patients in this population. But then there's a level of drug resistance that our pathogen has. And we have some, we have some mortality rate here. That actually does complicate things a little bit. This mortality rate, I realize that I've included here, complicates things because I've said that we're not going to have births or deaths. What I will assume, though, is that rather than there not be births and deaths, there's enough. Yeah, the way to get around this is essentially assume instead, actually, that births exactly balance the deaths coming in. So this here is actually slightly wrong. It doesn't ultimately end up changing things as far as we're concerned, really. Okay, so what's our naught? You can work out our naught just like we did before. This is going to be beta times by rho. We would have an S star here at our disease-free equilibrium. What's our disease-free equilibrium going to be in this population? Keep highlighting this, yeah? One, yeah, there we go. So that's just one. And then we divide by gamma times by 1 minus rho plus alpha. So this is our R naught. Note that also here, all we're doing really is we're taking the rate of new infections at our disease-free equilibrium, so what's coming into our infectious class, and dividing it by what's going out of our infectious class. We talked before about the average infectious period. This here is actually 1 over the average infectious period. So when we're working out our naught, we can work it out from our DIDT, but essentially what we're doing is we're saying, given that the whole population is susceptible except for this one infected individual, what's the rate at which they produce infections? And then we multiply that by their average infectious period, how long we expect them to be infectious for. So that's why we end up with beta rho here. S is equal to 1 at our disease-free equilibrium. And we multiply this by 1 over the average infection, 1 over this term here, which is the average infectious period, okay? Okay, it's also possible to show that we have a stable endemic equilibrium at beta of rho. Oh, sorry, I meant to write up here. In general, this S is just going to be 1 minus I. So we can get rid of R, we can eliminate our S from this equation. So we can work out our I star, and hence our S star is going to be beta of rho minus gamma times by 1 minus rho minus alpha over beta of rho, which is just 1 minus 1 over R naught. Note, obviously, this is only realistic if R naught is greater than 1. I leave you to check the stability as an exercise, if you so wish. Okay, so we're going to suppose our population is at its endemic equilibrium and this is stable. And like before, we're going to consider the fate of a rare mutant, IM, that has drug resistance rho m and transmission rate beta of rho m. So take a minute, write down what you think the equation is for invasion fitness of our rare mutant. I'm going to leave the equation up here. One word of caution, think about, although this is in terms of I's, think about which ones will be I stars and which ones will be IMs. So we can start from our DIDT equation. That's the only equation we've got in this system. If we want to write down our equation for invasion fitness, we can turn the IMs, the I's into IMs that are necessary. This one here is going to be an I star, not an IM, right? Because remember, this here is really just our S star. This is the density of susceptible, or proportion of the population that's susceptible in this population, okay? And this won't be varying with IM, because remember, we're always assuming that our mutant is having no effect on our resident population. So this is why this is an I star. We are going to have these rows become rho m's. And then we're thinking about our per capita growth rate when it's rare, so we divide through by IM. So this gives us our invasion fitness, W of rho m and rho. Actually simplify this a little bit further by noticing that 1 minus I star, or I star is equal to 1 minus 1 over R naught, which we had up here. So this is just going to be 1 over R naught. So this is going to be beta of rho m over R naught. I'll write this as R naught of rho, just so that we remember what this R naught refers to, our resident pathogen with drug resistance rho. And then we have the terms at the end. Minus gamma times by 1 minus rho m minus alpha. Okay. Hope you guys seasoned veterans now at finding invasion fitness. Okay, so let's think about when can our rare mutant invade the resident population? Well, for notational convenience, we're going to actually just label our base reproductive numbers for our resident and mutant strains as R0 with a little r for resident and R0 M for our mutant. So this R0 of rho here is now going to be R0 sub superscript R. Okay, so when do we get invasion? Well, invasion occurs when our invasion fitness is positive, right? This is our invasion exponent. Our mutant will grow exponentially when this is positive. So we've just worked out what this invasion fitness is. It's this here. So in other words, we need this term from the previous slide. This expression, I should say, to be positive. I've just said as well that we're going to relabel this as R0 of R. Okay, so taking these terms over to the other side, adding them to both sides and then dividing by them, you get beta of rho M over R0 superscript R times by gamma times by 1 minus rho M minus alpha, sorry, plus alpha. And this has to be greater than 1 for invasion. But note this here is our R0 for our mutant. Okay, if the whole population was susceptible, this is just our R0 for our mutant divided by our R0 for our resident. In other words, we get invasion whenever our R0 for our mutant is greater than our R0 for our resident. So just like in the previous examples, in this case, R0 is going to serve as a fitness proxy itself. We don't actually have to necessarily go through all the adaptive dynamics. We know that evolution is going to maximize R0 because whenever R0 for our mutant is greater than R0 for our resident, our mutant can invade. Like I said, evolution is going to maximize R0. R0 is a function of rho. Okay. So alternatively, we can consider the selection gradient. I've actually relabeled this here F because I realize as well, sometimes I might use capital F here just because the little s and the big S can get a bit confusing. So our selection gradient here, F of P, oh, sorry, F of rho, P. Well, this is just our invasion fitness. Take its derivative with respect to rho M. Evaluate it at rho M is equal to rho. We have our invasion fitness up here. So invasion fitness. If we take its derivative with respect to rho M, we're going to get beta prime of rho. We get beta prime of rho M, and then we're evaluating it so rho M is equal to rho. So we get beta prime of rho divided by R0 of rho plus gamma. We get a plus gamma here because we had a minus gamma, sorry, we had a plus gamma times by rho M. So that's linear in rho M. The alpha disappears because there's no rho M term, so we just end up with a plus gamma here. And therefore, a singular strategy, it must satisfy this selection gradient equal to 0. In other words, beta prime of rho must equal minus gamma as by R0 of rho. we have an equation that must be satisfied. So this should be rho stars. It's telling you something about how our the balance essentially that is occurring between increasing, the effects of increasing rho on decreasing our transmission rate must be offset by something to do with how much drug is being used, gamma, times by the change in our R naught as a result of changing rho. Again, there's a lot of this lately. I appreciate that it's because I don't want to take up class to do it, and you guys are always asking for exercises. So this is an exercise to show that this is either a CSS or a repeller. In other words, if you want to find its evolutionary stability and convergent stability, you can do. But we're going to assume that our trade-offs are such that we have a CSS. And we're going to explore quantitatively how affecting or changing the level of drug use, how much we change the drug use affects drug resistance evolution. We're going to get even more specific. We're actually going to assume that our trade-off looks like this. So beta of rho is equal to beta naught times by 1 minus rho squared. We see here that when rho is equal to 1, transmission would actually go to 0. That's not necessarily realistic. This is just one particular trade-off. If you do that, you end up with quadratic solutions for your singular strategy, but only one of these is biologically realistic. We end up with alpha plus gamma minus the square root of alpha times by alpha plus 2 gamma all over gamma is our singular strategy for rho. So we're assuming that this is a CSS, and we can show it's a CSS with this trade-off. We're skipping over that now just because we've done quite a lot of that, and I want to focus on quantitative outcomes. This is our optimal level of drug resistance. So what I want you guys to think about then is, given this is your level of drug resistance, let's just set, for simplicity, alpha equal to 1 to make this equation a little bit simpler. We need to have a go at sketching a graph of rho star and interpret it. Use it to interpret how drug resistance will evolve as antimicrobial drugs are used more frequently, in other words, as gamma increases. Okay. I'm shifting away from this qualitative prediction of it's a CSS or a branching point or a repeller. And you think about now, how do we say, okay, we've got some answer here for what our rho star is. How do we then interpret this for, say, a medical practitioner or a public health policymaker to say, okay, what happens as I increase my drug resistance, drug use, sorry. Let's have a go at sketching this and then try to think of what a biological interpretation would be for someone who doesn't have a mathematical background. I'll leave that like that.
We're sketching rho as a function of gamma.
Mm-hmm. Yeah, so rho is a function of gamma. Just I set alpha equal to 1 here just to make it simpler. Obviously, one could consider how this would vary as alpha varies as well. So we're setting alpha is equal to 1. So we're just going to have rho star is equal to 1 plus gamma minus the square root of 1 plus 2 gamma all over gamma. You could also write this as 1 plus 1 plus 1 minus 1 plus 2 gamma all in the square root over gamma. Okay, so what can we tell? Well, one thing we can do, let's see, what's the best way to do this? Start from this one here. One thing we can do is we can divide everything top and bottom by gamma. You're not sure what happens when gamma gets, say, very large. You get a 1 over gamma plus 1 minus the square root of 1 plus 2 gamma over gamma. And we get gamma over gamma on the denominator, so 1. So what happens when gamma gets very, very large? This is going to go to 0. And this is going to tend towards 0 as well. So you've got the square root of a large number over that large number. It's going to tend towards 0. So you're going to tend towards, here, this is going to tend towards 1 as gamma tends towards infinity. That should make some intuitive sense, right? The more drug that you're using, gamma is the amount of drug that we're using, the more drug we're using, as it gets very, very large, in other words, we're increasing our recovery rate, we would probably expect drug resistance to go up and increase, tend towards 1, yeah? I won't do it here just because we're running out of time. You can't just substitute in gamma is equal to 0 here to work out what happens when gamma is equal to 0. You can use L'Hopital's rule. We can differentiate the numerator, differentiate the denominator. And the limit of this is going to equal the limit of the differential of the numerator over the differential of the denominator, right? L'Hopital's rule. If you do that, you'll find that rho star tends towards 0 as gamma tends towards 0. L'Hopital's rule. And I'll leave that as an exercise. Again, that should make some biological sense, right? As we tend towards no drug resistance at all, sorry, no drug use at all, because drug resistance is costly, we should expect there to be no drug resistance evolving. There should be selection against drug resistance if you don't have any drugs being used. So piecing these together, we know that there's going to be some asymptote at rho is equal to 1. We know that when gamma is equal to 0, or as gamma tends towards 0, rho star is going to tend towards 0. Ends up looking like this. So what is our, if you're trying to interpret this for someone, we're saying, well, more drug use implies stronger selection for drug resistance. We can actually learn something here, though, as well, just about even a relatively small increase in drug resistance, say going from no drugs, drug use, going from no drugs to a small amount of drugs, leads to a relatively large increase in drug resistance, right? So this change here is quite large. If we went for the same unit increase over here of drug use, the change in drug resistance is not very large because it's asymptotic. Okay, so going from no drugs to a small amount of drugs has a relatively large impact on drug resistance. Okay, that's it for today. So just to recap, we've had a look at some qualitative and quantitative examples of pathogen evolution in the context of virulence and just now in terms of drug resistance. We've shown that changing the structure of our model in terms of the demography of how hosts' density dependence affects births and deaths can change our qualitative outcomes. We can potentially get coexistence now, diversification of our pathogen, coexistence of low and high virulent strains. And then we've also just shown quantitatively how drug resistance might evolve in response to the use of an antimicrobial drug. One thing to note is these are simplistic representations, okay? So these do not necessarily apply generally to every pathogen. They also, just to take this example here, this suggests that using more drugs is always going to make drug resistance evolve to a higher level. This is all at the moment deterministic. One of the key things is that we're not accounting for here is mutation supply that affects, whether we're able to have the mutations that will supply us to get towards this singular strategy. Typically, if you go hard with something like drug use to like antimicrobials and use them for the length of an infection, you will suppress mutation supply. So even though selection might be really strong for drug resistance, you're not necessarily getting the raw materials, the mutations that will allow you to get there. So this is only one side of that coin, if you like. Okay, that's it for today. Have a great week. Reminder, there is, the final homework assignment has been released. I have made it shorter than the other homework assignments because I know that you've got projects on as well at the moment. And yeah, don't leave your projects to the last minute. Okay.